Good afternoon, everybody. So we are continuing our discussion on the basic, the most important issues related to neutrinos. And last time we discussed in detail one of, I should say, the most important issue related to the effect of mass in neutrino physics. And if you remember, I would like to just to ask you to make some calculations, yeah? Take into account what we have discussed last time. So, you know, and this is like in a sense a repetition of what I told a week ago. So you know that the most important equation in neutrino physics is the problem on the mass. We know that the mass of neutrino is for sure not zero. This is a well-confirmed experimental fact. Well, I just recall why we are sure that it's not a zero. Because there are two problems. Of neutrinos. The southern neutrino problem, this is the flux measured here in detectors on the Earth, the southern neutrino fluxes. This is a problem. It's measured, experimentally measured about 3 times less than it should be if the standard model is okay. The standard model of electroweak interactions. Yeah. This is a big problem, and another problem is the atmospheric neutrino problem. Also, you know that there is another very important flux here in the Earth of neutrinos that are produced on the inner layers of atmosphere under the influence of cosmic rays. Electron, muon, and tau neutrinos appears, and it is possible to calculate the ratio of muon and electron neutrino fluxes in the Earth. And also there is a huge suppression in respect to what is predicted by the standard model of electroweak interactions of the muon flux. And these two problems can be solved only due to effect of mixing and oscillations. And just today, in maybe in 15 minutes, we shall start discussing with you these major effects in neutrino physics. And that's why we can say for sure that the mass of neutrino is not zero. But we do not know what is this value. This is a kind of paradox. We know this is for sure not zero, but nobody has measured a real value of this property of neutrino. And this is obviously the most important property of any particle, and also for neutrinos. What is the mass? And if you recall what we discussed, one of the possibility to measure, not realized up to now, the effective neutrino mass is to observe the endpoint of the electron that appear in the beta decay. And if you remember, we put, this is a Fourier plot. This is the number of neutrinos, and a value that is proportional to this depends. Really, we just put A, and this is a straight line. If this is Q, this is maximal value accessible for neutrinos. If you consider the decay of proton to a neutron to proton, electron plus electron antineutrinos, this Q will be equal to the mass difference between neutron and proton. Yeah? If you just consider nuclei, and as well as the tritium decay to helium, that will be the mass difference between the initial and daughter nuclei. Yeah. Well, and this line, this is the energy of neutrinos, and this is the mass. This is zero. Yeah. This is the mass of neutrino. And if the mass is not zero, if the mass is zero, we should have a small deviation. I just probably exaggerated. Here it is not visible on the lowest energies for neutrinos, but there is a huge difference. People hope to see. Yeah? And this is exactly. This is for the case of not zero mass, and this line is for mass equal to zero. Yeah, and people were looking for this particular endpoint of the energy spectrum of the beta decay electrons, and try to measure this. But obviously, as closer you are here, less events you have, obviously. Yeah? And I would like to formulate, probably I will move like this. No. How to lift it? Huh? Ah, this is not allowed. Okay, forbidden. Okay. We have to change slides. Okay, perfect. So, so we derive, as we call, the momentum spectrum of electron from beta decay. The momentum spectrum of beta decay electrons. We have derived last time. This is the number of electrons with a particular momentum with some spread of this value. What is the amount of electrons with this value around plus minus this small diapason? Yeah? This is a number of electrons. So this is spectrum. And we obtain the following. So this is a constant. B squared, this is a constant. Then this is a Fermi function that accounts for Coulomb interaction of the electron with the nuclei. This is depends on the structure of the decaying nuclei. Then Pe squared E minus P0 squared and square root. This is a factor that depends on the mass of neutrino. We use the system, this is not C squared, divided by the difference of energies squared dPe. This is the formula that we obtained last time. So, and I would like to ask you to estimate and to see. So I have to put plus, yeah, to move. Okay. Eh?
No.
Right? Okay, perfect, thank you. So, and the task. The task. So, the problem. Please solve this problem. Please show that the number of electrons let's put like the number of electrons with the very end of the spectrum. So this is the maximum energy minus delta E. So I just recall this. So I would like to recall, this is a Fourier plot. This is the end point, and this is delta E. So this is the number of electrons that have energy in very, very narrow band close to the end point of this. And this is the number of electrons. And please show that this is proportional to this energy band divided by maximum available energy to 3. This is what I would ask you to estimate, where delta E equals to Q minus energy of electrons. And as an example, Q for the tritium decay to helium is around 18.6 keV. And estimate. And let's take this energy band proportional to 2 eV. And just please find the number. It will be a miserable amount, very small amount of electrons. And this particular exercise will show how tiny and how difficult it is to produce these experiments. And if you remember, the best upper limit has been obtained by the cartoon collaboration, starting from 2019 till 2023, and they are running. And the best limit for neutrino mass is 0.8 eV. They cannot say, they do not see this deviation, but they can put a limit, an upper limit. So once again, we know that mass is not zero, but it is less than this. And also, I would like to emphasize in advance that this is just to put effective mass. Effective mass, because just in a moment we shall discuss with you that the flavour neutrinos that interact, that are produced and measured, because the measurements is due to some interactions, they have no mass. Because each flavour neutrino is a superposition of the states, real particle states of real particles, neutrinos with well-defined masses. So, but what is sensitive? The experiment is sensitive to some combination of fundamental masses of mass states of neutrinos multiplied by some constant coefficients. That we extract the value of these coefficients from experiments like solar neutrino experiment, atmospheric, etc., where we try to mimic or reproduce the visible fluxes. And just knowing how these neutrinos are produced due to the standard model, and then putting in the game this idea of mixing and oscillations, we have 3 parameters, the mixing angles, plus 2 mass square differences between 3 neutrinos, and we manipulate, we play with these 5 parameters and fix them from different types of experiments. Okay, so this is an addition to what we have discussed last time, and now I would like to discuss with you the most important effect, the effect of mixing in oscillations itself. I announced several times, but now I would like to go ahead and just to discuss this. So I have to put plus. This. Perfect. So, mixing and oscillations and just to put neutrino mixing and oscillations. We shall discuss, we start with the most simple case, which is very spectacular and which is quite easy to describe with the very simple formulas. So let's consider the electron and muon neutrinos. How we distinguish this, how we just mark this. From the Lagrangian of the Standard Model, we can specify, identify these fields. So these electron and muon neutrinos sometimes is flavour neutrinos, or the states of interaction. This is particular guys, the wave function of which participate in the Standard Model Lagrangian. So how we can distinguish, or just, there is, in the Standard Model, there is an interaction of electron with electron neutrino and with W boson. This is a particular term here in the Standard Model Lagrangian. Once you see electron, you can suppose that electron neutrino is participating in this process. In this particular block, this diagram, neutrino appears and disappears. So it's produced in the source and detected. Yeah? Similar diagram for identification of the muon, the second neutrino, muon neutrino, again W boson. So once in experiment there is a flux of neutrinos. For instance, there is an experiment, opera. Muon neutrinos were produced in CERN. They travel about 735 kilometers to Gran Sasso, and CERN, this is muon neutrinos, and then Gran Sasso lab in Italy, Italy. So the distance is about 735 kilometers, and here they detect a tau lepton somehow. Yeah? It means that tau neutrino arrived and double boson here. So that was an experiment, opera. In Gran Sasso. Gran Sasso. This is a mountain, Gran Sasso. There are two tunnels for cars here. So there was in the 70s, Italians decided to make easy to go from road to the sea. And they make these tunnels about 11 kilometers. And one very smart Italian physicist, Zecchicchi, still alive, he just proposed, once you make this very long tunnel with a huge job should be done, let's in the middle just have a special hole oriented to CERN. And in the 70s, the experiment was planned that somewhere many years after, the flux of muon neutrinos will be directed, because they just put direction exactly in a such way that muon neutrinos produced in CERN will come to this hole, and there is a huge installation about 50 meters long, about 6 or 10 meters high, and about 10 meters wide. This is big underground. This is the mount is about 3 kilometers, so just to protect from cosmic rays. Yeah, and they just succeeded after maybe 10 years of running. They succeeded to find tau neutrinos here, and that was one of the confirmation of the idea of the mixing and oscillations. Yeah, so this is the flavour neutrinos. Flavour neutrinos. Flavour neutrinos. Well, I use this French word. Yeah, sometimes you will see in literature flavor without you. Yeah, but I prefer this. Okay, and there is another vision on this phenomena, very complicated, which is neutrinos. We can introduce neutrinos with a particular masses. So, and we call it the mass states of neutrinos. Neutrino 1, neutrino 2. They have an exact determined, well-determined masses, M1 and M2. And in total, and so it means that for these neutrinos we can put the problem of propagation, and in principle we can solve this problem. So for these neutrinos we can write the Dirac equation. This is neutrino nu 1 in vacuum, and this is for neutrino 2 in vacuum. So if we know quantum field theory and smart enough, we can solve this problem and just find the solution of the equation of quantum mechanics of motion for this, because we know what is the mass of this particular neutrinos. But we don't know how they are produced and how they detected, because the Lagrangian that enable us to calculate the probability of appearance and probability of detective process in terms of flavor neutrinos. And but we should treat neutrinos as unique phenomena, very complicated. It's kind of dualism. When they produce a detected, they behave and can be described as flavor neutrinos. When they propagate, we should use mass states. Just to make everything together, we should say that these neutrinos, flavor, are a combination of these mass states. This is a guess, our guess. Yeah, but why we just put this guess axiom? Because there was no other way to solve two major neutrino problems: the stellar neutrino problem and the atmospheric neutrino problem. And also this idea of mixing and oscillations confirmed with different kind of experiments, not only with measuring of the stellar and atmospheric neutrinos. Also, this is an example. This is not a stellar neutrino, not an atmospheric neutrino. This is neutrino produced in the accelerator. And also we see that in the initial bunch flux of muon neutrinos, tau neutrinos appear. So this is another independent confirmation of this idea of mixing and oscillations. And there are a lot of other experiments that also confirm this idea. But most important starting point was the desire to solve the stellar and atmospheric neutrino problems. That was the initial point. And these problems appears approximately in the middle. The stellar neutrino problem appears has appeared in the middle of 60s, and atmospheric 10 years later. But as you remember, in 1957, Protokorov predicted that if the neutrino has no mass, neutrino is a mixture between neutrino and another type, antineutrino. That was Protokorov's idea. And it was implemented, just transferred solve the solar and atmospheric neutrino problem. So I have to put plus and what? Okay. So let's introduce the flavour neutrino. The flavour neutrino like a two-component. It can be whether electron or muon neutrino. And the mass states. Neutrino M, or sometimes people put P, physical neutrinos. Physical, it means that a real particle with a well-defined mass, you can just consider the propagation in space and time. Yeah? Physical. This is the mass states or physical states. Mass states, yeah? Physical neutrino. This is nu1, nu2, with the masses m1 and m2. And we should consider that M flavor not equal to to nu physical. They should be different, because we should find a solution for solar and atmospheric neutrino problems. Yeah. Well, then we just suppose that the flavour neutrino is some combination of the physical neutrino, yeah? Okay, and U is the mixing matrix. Matrix, yeah? And to reach, just to find an approach to the solution of the solar and atmospheric neutrino problem, we should find a solution for the problem of evolution of flavor neutrinos. What is happening when the flavor initial branch propagate in space and time to the detector? We should formulate the problem, the equation of evolution. And now we can choose any evolution equation, but the most reasonable to use a kind of Schrödinger evolution equation. Yeah. So, and we shall write the evolution equation for flavor neutrinos. So what is happening with them when they propagate from the source to the detector? And we postulate really I d over t, but as soon as we do not know the mass of flavor neutrinos, and mass is an important ingredient of any evolution equation, yeah, equation of motion, we should start with the problem of evolution of the states with a well-defined mass. Yeah? So, and we can start with the evolution of the physical neutrinos, because they have well-defined mass, and this is the Hamiltonian of evolution of the mass states of neutrinos. Yeah? So this is a question, yeah? And if we just know this equation, we postulate this equation. If we know this equation, we can, using the transformation, we can express the physical neutrinos in terms of flavor neutrinos and derive the evolution equations of flavor neutrinos. Yeah? What we should do on this way, we should specify somehow what is the expression for the mixing matrix. But we put it in a very general form, yeah? The most general form. Okay. So, and what about the Hamiltonian for the mass states? It is just the following: E1, 0, 0, E2, where E alpha, alpha equal to 1 or 2, all neutrinos in any experiments up to now are relativistic particles. And if we look on different neutrinos around us, it is proposed, it is expected that the only source of non-relativistic neutrinos is neutrinos from the very early of the universe. It's called the cosmological neutrinos. They come from very, very early moments of the Earth, yeah, of the universe. They are not relativistic, but nobody has yet observed them. There are 1 or 2 experiments aimed to observe these cosmological neutrinos, but up to now there is no any indication in favor. Yeah, obviously, when these neutrinos will be detected, people will get a Nobel Prize. Yeah, well, so it means that all other experiments, all other fluxes around us are super relativistic neutrinos. Therefore, we use the relativistic relation between energy and momentum. This is the Hamiltonian of evolution of mass states of neutrinos. Everything is well defined, and we can use this relativistic property of neutrinos, and we can expand the energy and take alpha, and take only into account only the first 2 terms. That will be modulus of momentum plus 1/2 m alpha squared divided by modulus of momentum. So we suppose that momentos are equal of 2 neutrinos. It is also a kind of paradox. We suppose 2 particles with different masses, but due to the fact that masses are very, very small, we always will account that energies are more or less equal and momenta are also more or less equal, because the difference is due to very, very small masses. So we put that the masses of neutrinos is much less than the energies of neutrinos. So this is a kind of not correct assumption, I should say, but it works. Yeah. Okay, and now we can make some exercise to extract the most important part from this Hamiltonian using these prescriptions and this agreement about that the neutrinos are relativistic, etc. And then we use this relation between physical and flavor neutrinos and derive a similar equation for evolution of the flavor neutrinos, and then we solve it and find the probability of detection of neutrino of different type. If, for instance, electron neutrinos were produced after the bunch traveled a distance in time, what will be the probability that neutrinos were converted to another flavor state? This was our program for today. So I put this one, yeah? Okay, perfect. So let's simplify, in a sense, this Hamiltonian. We can write that this is, again, expanded using the fact that neutrinos are relativistic. Put 1 divided by 2 modulus of momentum. And this is a matrix m1 squared, 0, 0, m2 squared. Yeah? So then we can, I would like to introduce the well-known Pauli matrices. Sigma 0 is 1, 0, 1. And we also need sigma 3. Sigma 3 equals to 1, 0, 0 minus 1. Okay? And we can decompose this and write it in the following way. So this is a unit matrix, yeah? We can write in the following way: the modulus of momentum plus m1 squared plus m2 squared divided by 4 modulus of momentum, okay, multiplied by this is sigma 0 minus, here I put very important delta m squared, mass square difference, I will just write exactly, divided by 2 or 4 modulus of momentum, sigma 3, where we introduce delta m squared equal to m2 squared minus m1 squared. This is the mass square difference of neutrinos. The mass of neutrinos. The mass square difference. This is a key value. It is play a very important role in the theory and in the experimental in interpretation of experimental data on neutrino fluxes. Mass square difference. Okay. So now let's the evolution of flavor neutrinos. We know the Hamiltonian, well, simplified, I should say, accounting for the fact that neutrinos are relativistic. We know of the Hamiltonian for evolution of mass states. We know of the relation between the mass and flavor states, and we can, using the evolution equation for the mass states, we can derive the evolution equation for the flavor states. Okay, what we have? We introduce that the flavor neutrinos are U mass states neutrinos. Yeah? Well, obviously, U should be unitary matrix because neutrinos does not evaporate, it disappeared to, so it means that there are two visions, two bases in describing this phenomena, and neutrinos are not escaping when we just make a transformation from one basis to another. That's why the matrix is unitary. It means U cross equal to U minus 1, yeah? So, and we can write from this we can just express the flavor state, the physical state, as U cross the flavor state. Yeah? And then we can put this decomposition or just this relation between physical and flavor states to initial equation of evolution for physical state and obtain the equation of evolution for flavor states. Yeah. So, and also we shall use the following very important property, that evolution in space can be related to evolution in time, because neutrinos are moving nearly with the maximal speed. Yeah. So it means that evolution in space and time, they are equal for ultra-relativistic neutrinos. Yeah. So, and then we obtain the following evolution equation for the flavor states. So, I, d, now we shall make this transformation to evolution in space. Yeah. U, correct? Neutrino flavor equals to H U cross neutrino flavor. Okay? Now we can make some exercises with these neutrinos. So I have to put this. Okay? Okay. Then the evolution of flavor neutrinos are following this equation: I d over dx flavor neutrino equals to U H U cross flavor neutrino. So, what we just suppose? We suppose that there is a relation between flavor and mass states. This relation is described by the unitary matrix, and also we suppose that neutrinos are relativistic. Yeah? Okay, now what about U? This is mixing matrix. We should somehow parameterize this matrix. Yeah? Well, it is possible to show that only one parameter is enough in this case, when you have two mass states and two flavor states. Yeah? And also using the properties. So, and we just introduce the mixing angle, the neutrino mixing angle. Theta. And we express this mixing matrix as cosine theta, sine theta minus sine theta, cosine theta. So it means that we introduce mixing of neutrinos. So each flavor neutrino, in our case there are only two, this is superposition of neutrino 1 cosine theta plus neutrino 2 sine theta. And for the second, muon neutrino is minus neutrino 1 sine theta plus neutrino 2 cosine theta. This is a mixing. So what was announced by words several times before, yeah? So each flavor neutrino is a superposition of the mass states. Just from here, it's obvious that if this guys has well-determined masses, this for sure have no well-determined mass, yeah? And as a result, so we cannot write a separate Dirac equations for electron immune neutrinos. You understand, yeah? If we just use two Dirac equations for neutrino 1, neutrino 2, and make and just instead nu 1, nu 2, you put nu e, nu mu, these two equations will be coupled. They were not separate, understand? So it means that there is no, these objects have no well-defined mass. We cannot put and obviously have nothing to solve, yeah? So it's not possible to describe equation of evolution, propagation of electron muon neutrinos. But we know how they interact with other particles. So the Lagrangian of weak interaction is determined, is written in terms of flavor neutrinos, but they have no masses. But propagation can be described in the usual way, in terms of nu 1, nu 2. Of course, if you just put the third one neutrino, we shall introduce the third tau neutrinos with a mass 3. Yeah? And there will be another mass square difference. Yeah? So there will be mass square difference m1, 2 squared, and delta m mass 1, 3 squared. Obviously, that the third one can be expressed in terms of the first two guys. So only 2 from 3 mass square differences are independent. Yeah. Okay. Now let's find this, and we call it Hamiltonian prime. This is the Hamiltonian of evolution of flavor neutrinos. Yeah, let's find this. So H prime equals to U H U prime. So, yeah, I put here, just before to continue, I just recall the following. We have to calculate sigma 0, U. This is unit matrix, and U multiplied by U is unit matrix, yeah? This is unit matrix, yeah? So we also have to calculate U sigma 3 U cross. So I just recall that U cross equal to U complex conjugate transform, yeah? This is definition, yeah? Yeah, okay? So, equals to, let's just put this, I will continue it here. Let's introduce S equal to sine theta, C equal to cosine theta, to make our calculations shorter, yeah? Cosine and sine theta. So, and just this is our agreement, our new notation, and I just will write in detail cosine theta sine theta minus sine theta cosine theta. This is u, yeah? Then I write this sigma 3 matrix, 1, 0, 0, minus 1, and then I calculate du cross. Conjugate is nothing because everything is real, yeah, all these numbers, yeah, and we only have to transform this matrix. This is cosine minus sine, sine, cosine, and then we have to make some calculations here. So minus cosine sine, sine cosine, cosine minus sine, sine cosine equals to, can be expressed as a cosine of double theta and sine double theta. So the angle doubled, yeah, if you recall what we have studied in the primary school, yeah, if you remember. Yeah? Okay, that is minus, I don't know why I put minus here, minus cosine double theta, then sine double theta, sine double theta, and cosine double theta. Okay, this is very, very, very straightforward calculations, and we can continue and change our board to a new one. So finally, after these manipulations, we get that H prime equals to modulus of momentum plus the sum of mass squared, m1 squared, divided by 4 modulus of momentum or energy, multiplied by the unit matrix, yeah, plus mass square difference divided by 4 modulus of momentum. And here, what we have just obtained on the previous our slide, or minus cosine double theta, sine theta, double theta, sine double theta, cosine double theta. So, and as soon as this Hamiltonian doesn't depend on x, we can easily write formal solution for this equation. Hamiltonian is not dependent on the x, yeah? Then we can integrate the evolution equation for flavor neutrinos. And we can get that flavor neutrinos in some coordinate x. You understand that x, we parameterize the coordinate along the propagation of neutrino, yeah? So this is the source, and this is a detector, and this is coordinate x, yeah? So we can write that this is equal to E my exponent minus I H prime X multiply on the initial flavor state in the coordinate x RAM equal to 0 in the source. Yeah? This is a solution. Because Hamiltonian H prime doesn't depend on the coordinate, a formal solution. Now, what we shall do further? Then we would like to calculate the amplitude, the probability of transition of neutrino from one state to another, from electron state to muon state. And so it means that part of Hamiltonian that is proportional, it doesn't depend on the coefficient, proportional to the unit matrix, have any influence and doesn't change the initial flavor. So if we just put on the scene the problem of evolution or change of flavor, this part is not important, because the probability is the modulus of the amplitude. And if you put the modulus, this part will run away, give 1, obviously. Yeah? So it means that only this part matters for the problem of the probability to observe neutrino of a different flavor in respect to the flavor it was produced initially. Yeah? So we can just forget about this, just in our straightforward discussions. Yeah? So, and we can write that H prime equals to, we can introduce the third matrix, sigma 1, that is 0, 1, 1, 0. So, and we can write that this is equal to m mass square difference divided by 4. I put here energy, so I just introduce energy is approximately equal to momentum, yeah, of neutrinos, because it's a relativistic particle, yeah. I just put, instead of modulus of momentum, I put the energy of neutrino, yeah. Also, this is a kind of contradictory assumption. There are two particles with equal energies, with equal momenta, but with different masses. This is exactly not true. But if we suppose that the mass of each these mass states much smaller than the energy of the modulus of momentum, it means that this is more or less okay. This is a kind of approximation, yeah? A kind of approximation that we use it. Okay, and if we just introduce this matrix, we shall have the following: is sigma 1 multiplied by sine double theta minus sigma 3 cosine double theta. Yeah? Well, I would like quite a simple and quite good expression, yeah? Not complicated at all. And then we can write, using this expression for this Hamiltonian, we can write that the solution for the flavor neutrino in x point is given by the exponent minus I mass square difference divided by 4 energies of neutrinos x, and here this combination sigma 1 sine double theta minus sigma 3 cosine double theta. Okay, this is solution. Now I would like to address to your notion how to operate with these guys. So we know this is a matrix. We know how this matrix acts on the wave function. And if this operator matrix is in the definition of the exponent, how we just operate with this guy? We do not know really if the matrix enters the exponent, yeah? So, but we can expand in rows the exponent, and using the properties of the Pauli sigma matrices, we can simplify this. I put here, and I would like to recall, probably this is a normal quantum mechanics, yeah? Do you know how to operate with this? More or less. No? Okay, I just recall. So, some addition, yeah? So, there are very simple things equal to 1 plus ix 1 factorial plus ix squared 2 factorial plus x 3 factorial. So, okay. Then we know how to expand cosine. This is x minus x squared divided by etc. Then sine x is cosine is 1. Yeah, sorry. X minus x 3 divided by 3 factorial, etc. Yeah. So it means that exponent I phi equals to cosine plus I sine phi. Yeah. So then using all this stuff, we can write what we are looking for our calculations. I, some coefficient alpha multiplied by I, sigma I. We decompose to the odd or even terms. This is a sum n equal to 0 to infinity to I to double n sigma I double n divided by double n factorial alpha to n plus sum to infinity I to n plus 1 divided by 2n plus 1 factorial sigma matrix 2n plus 1 alpha 2n plus 1. So we know that sigma I squared equal to 1, okay, etc. Well, and then we get that, finally, we get that exponent I alpha sigma, if you just put vector here, equals to unit matrix cosine alpha plus I sigma vector sine alpha. That what we really we were looking for, not this particular, but with minus exponent minus I alpha sigma vector equals to unit matrix cosine alpha minus I sigma vector sine alpha. This is exactly what is needed for our calculations, and this is Nobel's transformations. that you very well known from quantum mechanics, I suppose, yeah? So, and now only one step ahead should be done to write a solution, to derive the exact formula for probability to observe, let's say, muon neutrino in the initial flux of electron neutrinos, the probability of oscillations. Okay? I can move it. Yeah? Okay? So, using these very simple formulas, we can write that the flavor neutrino in the point characterized by coordinate x equals to, I just repeat, I mass square difference of, okay, I just mass square, I cannot put that mass square difference divided by 4 energy of neutrinos, x, don't forget this x, sigma 1 sine double theta minus sigma 3 cosine double theta, okay? And the initial flavor neutrino. So, just using the formulas that we have just derived, I can write that this is cosine mass square difference divided by 4 energies, x, minus sigma 1 sine double theta minus sigma 3 cosine double theta minus sigma 3 cosine double theta. This is bracket, so multiply by sine mass square difference divided by 4 energy x, and we close it, and also not forget the initial neutrino flavor state. Okay, that's all. So we have found how the initial state in the point determined in the point x ram equal to 0 in the source, how it transforms once neutrino travel to the coordinate equal to x, not equal to 0. This is solution of evolution equation for the flavor neutrinos. Okay, now we can put forward a problem and write a solution. What is the probability to observe a neutrino of a different flavor in respect of the flavor it was produced after the flux of neutrinos travel a distance from x rounded to 0 to x? The probability, so let's make concrete and define the probability to observe muon neutrino in the initial flux of electron neutrino. The probability of oscillations. This is the probability of oscillations between different flavor neutrino states. This is using the quantum mechanical prescriptions, yeah?
Doesn't equal to what?
This is a quotation, this is, we are happy that we just derive, that we finally derived to the end, yeah? This is quite happy. Okay, so the probability to observe or to, so the probability to observe muon neutrino in the initial flux of electroneutrinos, yeah? Like in the sun. In the sun, neutrinos are mostly produced in the electron flavor, and in the detector, if you remember, Davis measured 1/3 of amount. If standard model is okay, so it means that there is no mixing or oscillations, and if the theory of sun, as we call it, the standard Sala model, is working perfectly. But please believe me that the standard model of the sun is a perfect theory. There is no problem with the amount of neutrinos, electroneutrinos produced in the sun, because we know now from, again, there is an experimental verification confirmation that this Bacall, this is an American scientist who for many years, he has passed away, his collaborators, he just developed the Sala neutrino, the standard model of the Sala standard model. It's a very complicated theory that produced as one of outcome is the prediction of what amount of electroneutrinos evaporate or just escape the sun per second. And this is a good theory. But Davis measured only 1/3. And because 2/3 were transformed to muon and tau neutrinos. And this is the probability of amount of muon neutrinos in the initial flux of electroneutrinos. Of course, this is a simplified version because we consider only 2 flavor and 2 mass states. And for this particular case, it is possible to write very simple formulas on the blackboard, or just on this, not a blackboard, a whiteboard, yeah? But if you had put the third one, the mixing matrix will be 3 by 3. There are additional mixing angles, at least one more mass square differences, and the formulas become very fat and very difficult to write. But it's also possible to write, and in one of the next lectures I will show you the mixing matrix for 3 mass states and 3 flavor neutrinos. But the point is that the solution for the Sala neutrino problem mostly can be reproduced by transition of electron to muon neutrino, mostly. Some parts will go to tau, but it's a small contribution. And on the other hand, the solution of the atmospheric neutrinos is mostly given by the transition of muon neutrinos to tau neutrinos. And the contribution to transition muon to electron gives a very small portion. So it means that just in the beginning, it was quite enough to separate 2 transitions, electron to muon neutrino and muon to tau, because the third, in both cases, type of neutrino gives some additional terms that even were not important for interpretation of the third set of experiments. Now it is important because experiments become very sensitive, and now 3 by 3 mixing matrix should be used. Okay, so this is according to the rules of quantum mechanics. This is the square of the amplitude. The square of the amplitude. This is the muon neutrino, and this is the electron neutrino in the coordinate point x. The coordinate x. But we have found if you just put, instead of f, put E, that will be evolution of electron neutrino to muon neutrino, yeah, obviously. So let's continue here. So we put modulus 0, 1. This is the projection to the muon state, you remember, yeah? The flavor, we introduce the flavor as electron to muon. So the muon neutrino is 0, 1, obviously, yeah? So sigma 1 sine double theta sine mass square difference divided by E X electron neutrino 1 0 squared. Obviously, this guy doesn't contribute. Yeah, it's washed out. So, equal to sine squared double theta multiply by sine squared mass square difference divided by 4 energies x. I just write once again, this is the probability to observe neutrino in the flavor muon flavor after the initial bunch composed totally of electron neutrino travels the distance from x equal to 0 to some fixed x. This is the probability of neutrino oscillation. This is a flavor neutrino oscillation. This guy is termed the amplitude of oscillation. It's a fixed, it's a constant. This is amplitude. I cannot move, yeah? How to? Okay, let's. Finally, the probability of neutrino flavor oscillations. So, the probability of transition or oscillation of muon neutrinos after electron neutrinos to flavor is sine double theta mixing sine squared mass square difference divided by 4 energies x. Why there is oscillations? Because if you just put like this, it will be like something like this, yeah? And the amplitude is exactly sine double theta. This is the amplitude, and this is how it's changing as sine squared some coefficient multiplied by the distance. That's why it is oscillations, yeah? And this term, this guy is called the amplitude. Of oscillations. And now we can see quite easily that if we implement this hypothesis that the only chance to explain or solve the solar neutrino problem and atmospheric neutrino problem, and if you remember in 2015 the Nobel Prize was given for the discovery of neutrino oscillations. This is a formulation from the statement of the Swedish Academy of Sciences. For discovery of neutrino oscillation that confirms that the mass of neutrino is not 0. So, the discovery of neutrino, this is needed to explain the solar neutrino problem and atmospheric neutrino problem. There was no other way out. The only chance, because all other possibilities were excluded experimentally. And why it confirms that neutrino has not 0 mass? Because if the mass of neutrino is 0, obviously delta m squared equal to m minus m1 squared will be 0. Yeah? But I would say that from my point of view, it should have been added that not only that the mass of neutrino are not zero, but it is very important that the masses of neutrinos are not equal to each other. You understand, yeah? Because they cannot, even in the case of two neutrinos, they can be not zero, but if they are equal, again, mass-square difference will be zero. So it means that the statement is not complete. And if you take into account that there are three types of neutrinos, now we can say, and also the solution that are not, so obviously that not three masses is excluded, that all three masses are zero. Then it is excluded that all three masses are not zero but equal. Three different masses, but they are equal. So it means that at least two masses are not equal. So you need to have two not equal to zero mass-square differences in three guys. It means that at least two masses are not, so all masses are not zero, and it's not enough. At least two are different. And also it is possible that one is zero, but two are different, not equal to each other. Okay? You have to generate two different mass-square differences, not zero, because one is used to explain the Solar-Neutrino problem, another on the same basis, on using the hypothesis or not phenomena. Now it's not a hypothesis, it's a phenomenon. It's comfort hypothesis. Yeah, one is used mass-square difference for solving the Solar-Neutrino problem, and another not zero mass-square difference. Another one is used should be used to solve the atmospheric neutrino problem. So nowadays the picture is like this: masses are not zero, okay. Masses are not equal, and at least two are different. Yeah? And two can be equal to each other, two. But the third one should not be equal. You see? This is the story. Very simple phenomena. Everything was, this phenomena was predicted by Bruno Pontecorvo. In 1957, a distinguished Soviet and Russian physicist of Italian origin. And we are very happy that Pontecorvo, for 20 years, from 1966 to 1986, was the staff member of the Faculty of Physics of the Moscow State University. And also there is a kind of very personal. This particular year is the year of my birth. Okay, yeah. So this is one of the most spectacular, I should say, phenomena in neutrino physics. And obviously, it is not within the Standard Model. Why we are saying that the neutrino open a window to new physics? Because in the Standard Model, the mass of neutrino equal to zero. And there is no mixing, no oscillation, and there is no difference between flavor and mass states. All states are zero, so there are mass states with zero mass, and they are identical to flavor states. This is the story for the Standard Model. So there is no room for solution of the solar and atmospheric neutrino problem if you are confined within the Standard Model. So, and my final remark, neutrino are indeed spectacular object in particle physics, the only one known particle that exhibit well-confirmed experimentally properties beyond the Standard Model. There is no other particle that should be described by the theory beyond the standard model. Of course, you say there are dark matter, dark energy, etc. There are a numerous amount of hypothetical particles that theorists use to investigate, to produce the properties, etc. Ask our friends from accelerator physics to confirm, just to observe, but they are not observed. Like axions, like supersymmetric particles, some Z-prime bosons, some exotic particles, but they are not observed. Nobody knows. We can say that the objects exist when once an experimentalist will show that this particle really exists. But neutrinos do exist, neutrinos, yeah? But the properties are beyond the standard model. That's all. Thank you.